Hi, welcome back to this video series on SMT solvers. Today I'm going to talk about an interesting problem in which we will ask the computer to come up with a C program for us based on a list of example input-output pairs we give to the specification. Okay, so what we would like to do is this. We wanted to infer a box. Okay, we don't really know what's going on inside the box, but we do know how the box should behave. We send some input, we look at the output. Okay, and the output that's coming out from the box must match what we would like to see. Okay, so given a bunch of examples, basically what I'm saying is you are giving some input and output, right? To the automated reasoning engine. Okay, so given input output pairs, the automated engine should come up with the program for us. Okay, let's say the function f, the magic function f should be inferred just based on input output pairs that we give to the reasoning engine. Okay, that's the problem that I'm interested in. Okay, and there are many cases where you would like such a tool to help you, right? For example, if you're writing a complex algorithm, you kind of know what the input and output pairs are, but you don't really know how to come up with an F in a more compact way. Sometimes you have constraints on how the F should look like. For the example that I'm going to talk about, I'm going to put a lot of constraints on what type of syntax elements are allowed. For example, I don't allow if statements. I don't allow a greater than, less than. As I put some more detailed constraints later, I will show you that. But that's basically what I'm going to talk about now. So given input output pairs, I would like to infer F. Okay. So for that, I wrote a simple a problem statement just to explain to you the idea, and then we will get into the details. Okay, that's the plan. Okay. So I will show you the problem now. The problem is formulated like this. We are asked to write a program. I mean, the computer should write a program actually that will return 1 if any bit of x is equal to 1. Okay. For example, if the input is say the input x is 0, what should be the output then? Output should be 0 because there's no bit turned on. If x is say 3, output should be 1. So this is a very simple task. You just write a if statement saying if your x is not equal to 0, return 1, otherwise return 0, right? So you could easily write it in one line, but that's not what I'm after. I'm after a program which has additional properties. Okay, we are allowed to use bit level operations. What I mean by bit level operations is left shift, right shift, bitwise XOR, and that kind of bitwise operations. We are not allowed to use though if then else statement, Boolean logic operations like and or not. Okay, Boolean and not bitwise and, by the way, just to be clear. Okay, and we are also not allowed to use equal or not equal. So we are having lots of constraints. Okay, and we are not allowed to use even I forgot to add this. We are not even allowed to add the not operator that we use. Well, this is basically the same as here. Okay, this is the not, right? Okay, so it is covered. Okay, so this is the not allowed part, right? And what is allowed is basically bit level operations that I have highlighted here. Okay, so how do we handle this? Okay, well, one more constraint is that the shift amount, when you do shift left, shift right, you specify how many bits. You must make sure that you don't shift more than the size of the word. Okay, so if you are dealing with say integer which takes say 32-bit for a moment, okay, then your shift cannot be more than you can't write it like this. This is not allowed. Okay, it has to be this is not allowed, because 32 is already more than the word size in terms of what you can pass here, right? It has to be at most this. Okay, it has to be at most this. And of course, you cannot put negative also because those are all undefined behaviors. That's why we put the restriction. Okay, so now we have a lot of restrictions to satisfy. So I encourage you to pause and think about it. It's not a trivial problem because you need to have a deeper understanding of Boolean logics and all the other constraints they have added here to make it more harder. But I'm going to let the computer come up with this little bit cheating now, right? So what I did is actually model this, right, in in a syntax guided synthesis approach, syntax. So here is the approach. I will highlight just the high level overview, and then I will talk about the details of how I came up with the specification to show you the idea. Okay. So I wanted to come up with the any bit on function, right? That's basically my goal. And that function will take an x as an input, a 32-bit integer as an input, and it comes up with the number 1 or 0 as the output. Okay, that's basically the high level interface, any bit on. But the grammar is based on the problem statement. We are allowed to use add, or, and, bitwise or, bitwise XOR, bitwise left shift, bitwise right shift, right? Those are some of the operations that we are allowed to use. Okay. So it's not complete, but it's good. I think we can also add. I don't remember. Let me check this. I think it's called. Yeah, something like this. Okay. So these are all the different operations that we are allowed to use. And now let's see whether we can come up with a program automatically. Okay. There is one thing that I didn't represent in this grammar very compactly is the shift amount, right? I didn't explore how to specify the possible shift limits, so I just made it hard-coded like this. But this is not just complicated at all, right? You just write numbers from 0 to 15, right? That's what I wrote it here. Maybe there is a way to express this in a much more compact way. I have to explore it anyway. So now the most important part though is that how do we sort of train the program and give some examples? Let's say we don't know the way to formalize it, right? For example, you wanted to just play with the input and outputs and see the behavior. Say let's take a simple example. Okay. So what I'm going to do is say I will make it like this. I will give some input output pairs, right? When my input is 0, I expect the program to return 0. When my input is 1, I expect the program to return 1. But this may be too much or too little rather for this inference engine, right? Let's see whether it can come up with anything useful for us. It will not, right? Because there is no way we specified to count whether any place has a bit 1 or all bits are 0. We didn't specify that in the example, right? So the inference engine just said, okay, your input and outputs are the same. If you send me X, I will give you back X, which is true for those two example scenarios, right? Because I just passed 0 and I expect 0. When I pass 1, I expect 1. So there is no way it can come up with something magically, right? So we should add a couple of more examples and see what happens. Okay, I added a couple of more examples and I will show you now my examples. Okay, so I added 3 more examples, and now let's see whether it can come up with anything clever. Okay, it takes a few seconds to explore the state space of all possibilities. So a little bit patience is fine because it's going to come up with something good. Okay, in the meantime, I want to tell you that this program that you're going to see will be free of if then else statements. Okay, it will not have anything like less than, greater than, those kinds of operations as well. So it's much faster, much more efficient rather. Okay. Yeah, it could be faster also to some extent if then else is considered slow in some machines. Okay, so it's now exploring the combinations of possibilities from the grammar specification. So it should come out anytime soon. So just for your information, the tool that I'm using for this particular analysis is called the CVC4, which is a symbolic or satisfiability modulo theory tool, and it has the capability to do syntax guided reference in inference of programs. That's what I'm using for. Okay, now here is the output. Okay, let me parse this output for you. So what it means is this, right? The program takes 2 inputs, right? No, sorry. The program takes only 1 input. Here is the input X, right? This is the input X, and here is the function name, of course, or a program name. Okay, so what you're seeing here is that the program takes X as an input and sends you back another bit vector as output. Okay, so what is the program now? The program itself is basically this part, right? Okay, what is this part? Let me parse this for you. So it's nothing but neg means negative. Okay, so negative x, right? What are we doing with bitwise XOR? That means you have x in the front and you do bitwise XOR, right? With the minus x. And then what are we doing? We are doing shift right of this whole thing by how many positions? 1, 2, 3, 4, 5 positions. That means 2 power 5 minus 1, which is 31 positions. Okay, so this is basically what the program is. Okay, the program is nothing but x XOR. So let me write it clearly here. X, right? XOR. This is XOR minus x, and I encourage you to now stop and think, what is the meaning of x XOR minus x? And then we're doing right shift by 31. At this point, we don't even know whether this is correct. So we just got an expression based on a few runs, right? We gave some examples. We don't really know whether this is correct. So we can add more examples and see whether there is any change in the formula. Okay, if there is no change in the formula, what can we confirm? We can confirm whether we can confirm one thing, right? We tried many examples, and the program actually converged to that particular expression, the inference program. So our example seems to be reasonably good in terms of covering the space of possibilities. So what I can also do is now go back to the program, right, and see whether we can specify something more precisely. Okay. Remember, my goal is to learn a program based on example. So I gave this bunch of expressions, and I learned a reasonably good program, which appeared to sort of address all of these, right? So what is the next thing we can do? And the next thing we can do is try more examples, right? Try one more example, two more examples, and so on. Okay, so what I'm going to do is slightly different now. I'm going to just make a very generic expression now. Okay, more formula oriented expression. Okay, so I'm going to do like this way. So I will copy this. So here is what I wrote here, right? What I wrote, this is basically, I'll comment it now. We don't need this example for a moment. What I'm going to do is show you how we can infer based on a specification which is independent of concrete inputs, right? What I'm saying here is simple. I'm saying take an input x, we don't know what it is. The behavior of the function that we are going to infer must satisfy this property. The return value from any bit on function is 0 whenever the input is 0. Otherwise, the return value is 1. That's what we expect the program to do. So let's see whether we can infer this. Hopefully, it's going to infer something. And then we can compare also between these two expressions. The more bit size, the more time it takes. Actually, on the online versions of CVC4, I can do it on a smaller bit level bit vector size, which makes it much faster. But for some reason, the offline versions do not allow me to specify small bit vectors. That's the reason I picked 32-bit. I could have actually, in fact, put to 8-bit. Maybe that would have been much faster. On the online version, you can try with 4-bit, 5-bit, even more faster. Okay. Anyway, that's not the point here. The point is to infer a non-trivial expression, right, based on constraints. Okay. So hopefully this is going to come out soon, and we can see how the inferred program looked like for the general specification we gave. We have it, and what we have is pretty much similar to what we already saw through example learning. Learning with example is not that bad, right? We got pretty much the same. Only difference though is this XOR here is replaced by OR. That's the only difference. But let's see whether that difference really matters or not, right? Okay, well, the constant remains the same, so there's no difference. So let me explain why there's no difference between these two, although it's called XR here and it's a regular R here. So if you think about the behavior of this function f that we are trying to infer, what type of function we are inferring? We are inferring a very simple function that will give us a value 0 or 1. It returns 0 only if the input is 0, right? Otherwise it returns 1, that's all. So what is the meaning of minus x in terms of bit pattern? That's the important thing I would like to discuss now. So let me go to the whiteboard and explain the meaning of minus x, okay, by taking an example for you. So let's take example, simple example. Let's just take a 4-bit number, okay? Just a random 4-bit number. I just pick one 4-bit number. Let's see this example. This is number 4 in terms of base 10, right? What is minus x? Minus x is nothing but, what is minus x? Okay, so there is an interesting property I would like to write it here separately. Minus x is nothing but 1's complement of x, right? Plus 1. Okay, so plus 1. This is minus x. Okay, this is an important property. So if you apply that to this x, what will be the complement of x? The complement of x is 1, 0, 1, 1, right? And if I add 1 to it, it will become 1, 1, 0, 0, right? It will become 1, 1, 1, 1, 0. Okay, one moment. I think I made a mistake here. So what is minus x? Minus x is basically complement of x. Let me just clear this a little bit. Erase this. Okay. Okay. So what is minus x? First, I need to take a 1's complement of x, of course. So let me just first do 1's complement of x instead of minus x. Okay. This is 1's complement. Okay. No minus. So 1's complement of x is 1, 0, 1, 1. And if you add 1 to it, so we're going to add 1 to it, right? So what will happen now is 0, carry over is 1. So it's going to be 0. And then it will be 1. And then you have 1. So what you have is, this is nothing but minus x. Okay, so this is minus x. So minus x is 1, 1, 0, 0. So I was correct. Okay. So what you are seeing here is that minus x has an interesting property that it just takes your original x, right? All the rightmost bits are actually copied as it is until the very first one. Okay, that makes sense if you think about it. Minus x basically transforms this exact content as it is. Okay, and then the rest basically is complemented, right? 0 becomes 1. Okay, so now if I just take the learned formula, for the second formula was like this, right? It was like it said f of x is nothing but my x, right? Bitwise or with minus x. Okay, now what is bitwise? Okay, let me finish this. And then right shift by 31 position. Okay, so let me finish x xr with minus x. Okay, what is x xr with not xr, sorry, r. Okay, what is this? This is nothing but 1. Okay, and r doesn't change anything, so we just have a copy of the rest. Okay, so this is the x or with minus x. Okay, now if you just get rid of all the bits other than the most significant bit, what will happen? You'll get 1, right? That's basically the purpose of this operation, right? Shift operation. So this is the correct answer because our input is non-zero. So this is correct answer. So you can think about the case when x is 0 now. When x is 0, you can now do much more easier analysis, because when x is 0, what is minus x? Minus x is also 0, because minus x is nothing but complement of x is just made of all ones, and when you add 1 to it, you get 0 again in modular arithmetic. Okay, so minus x is also 0. That means x or with the minus x is also 0. So the answer is also 0 after shifting it by 31 position. Okay, so which is the correct answer. Okay, that's basically it. So as you can see, it was not that straightforward to come up with such an expression automatically, right? We of course have to specify the grammar a little bit, but it's much more challenging for humans to come up with this expression. I think it was not that easy to say, okay, if you come up with this expression like this, x minus x bitwise or 31 will give you the answer that you're seeking for. I don't think that's that easy. By the way, the or and the xr can be replaced, because in this case, remember the minus x, what the minus x does is it copies everything from the least significant bit until the first bit that has the value 1, including that, and the rest are just complemented. Therefore, when you do XOR, right, the matching bits got cancelled out, because XOR will cancel those matching bits. But then the left ones are just complements anyways. Therefore, when you XOR complements, you get 1, right? And therefore, this is still okay if you replace this by x XOR with minus x. 31, as far as I can tell. Okay, this is basically the idea of this is XOR. Okay, just to be clear, this is the idea of learning by example, right? We gave some example to the system. So we want the system to come up with this box for us, right? We have the magic F in the box. We know how the system should behave for input I, right? We know the system should give us the output O. We trained the system for many I's and O's, right? And we said, okay, system, come up with an F that satisfies what we gave. So essentially, that's the idea of example guided synthesis, if you want to call it that way. I also felt that if you know the specification, in some cases it's easier to specify the specification rather than specifying all the examples. Then it's much more easier, and furthermore, you can put whatever constraints you like to have, right? So for example, you could just say, well, let me go back to my example, right? Suppose you say, I don't like to see some operations, right? You could easily just go to the grammar, right, and say, I don't like, I'm just going to show an example, right? I'm saying, okay, for example, I don't like XOR for whatever reason. So you can just comment this, right? And then ask the engine to come up with, maybe I don't like, say, this shift right operation, okay? So we can just comment this, and then we can ask the system to explore the space of possibilities. We can try to come up with anything more or less we would like to have. Of course, it has to be meaningful. Maybe some operations cannot be realized without certain operations, right? That's a fundamental constraint of Boolean algebra. Then you can actually automatically infer once you have that grammar in place, of course. Okay, so it's going to take a little bit of time. I should have put, okay, now it's there. So you see, now it avoided XOR, it just used the bitwise OR. Okay, suppose you say, let me confirm whether I can get only through XOR, okay, and not using OR. You can do that, of course. So it's inferring a program as we speak using the CVC4 synthesizer, syntax guided synthesizer. I'm sure there are many other options that will make this inference much more faster. I have not done detailed analysis of that. I plan to do it later. But my goal is to show you how you could derive programs based on input-output examples. These are non-trivial programs, okay? You have constraints, lots of constraints. You said you're not allowed to use equal, you're not allowed to use not equal. not allowed to use if statements, just only a few things that you're allowed to, in fact. So that's why it's a bit of a challenge, in my opinion. Okay, let's see whether we can obtain a new model based on the constraints that we just added. It should come out soon, hopefully. It seems interesting that it's getting stuck somewhere. I don't really know where it is. Let's see. Hopefully it's coming soon. Oh, I didn't press the enter button, did I? Okay, we'll wait for a minute and then go back to the program maybe and delete or add some new constraints. Okay, it came back. So as you can see here, this time it came back with a different model, right? It used the shift right, but instead of using the OR and negation, it used actually negation and bitwise and to come up with this model. Well, they must be same, otherwise the program won't come up with another program like this. So as you can see that you can play with your grammar and then get different examples like this inferred for you. Okay, that's basically what I wanted to share. Thank you very much.